Okay, in this video we're going to talk about reaction mechanisms, or kind of the process of how these reactions go. We're still talking about kinetics, so we're still talking about how fast, and so now we're going to talk about, for mechanisms, what that means in terms of affecting the speed of the reaction. All right, reaction mechanisms. There is a series of steps in a chemical reaction, and we've seen this. When we talk about Hess's law with all the energy steps, this is the same thing. This is, every single species that shows up. So even though a reaction appears simple, the equation doesn't really show us any detail about how it actually takes place. Or in other words, what are the parts and pieces? How are the electrons being transferred if it's redox? How are the ions rearranging themselves? What is the chemistry that's taking place? For example, this is our overall reaction of the reaction of nitrogen dioxide and carbon monoxide to give us nitrogen monoxide and carbon dioxide. Okay, there's really two steps that this has to take place in. First of all, you have the two nitrogen dioxides combining to form one nitrogen trioxide and one nitrogen monoxide, and then that nitrogen trioxide that's left reacts with carbon monoxide to make nitrogen dioxide and carbon dioxide. So what you end up with is being able to cancel out what are called the intermediates. And we've seen this where you want the overall thing to balance, to give you your final reaction, so you need to cancel out the things that are called intermediates that you don't want. So if you cross off the intermediates of the nitrogen trioxide and the nitrogen dioxide, you're left with your overall reaction. You're left with the nitrogen dioxide plus the carbon monoxide. I realize I'm losing you because I'm saying all these oxides, but you essentially get rid of the things that aren't in the end of reaction. So an intermediate we're going to define as a species that is formed and then consumed in their steps, so it does not appear in the overall reaction, and it appears as a product and then a reactant. So it's kind of like algebra, that if it's on both sides, we can cancel it out and we can cross it off. Now, a catalyst is something that we keep throwing around. A catalyst is a species used to speed up a reaction. It's also not in the overall reaction. We've written it above the arrow. The reality of it is when you have these reaction mechanisms and true reaction mechanisms, we really can put it as both a reactant and a product. It's just typically when we're writing reactions, we usually write net ionics, so we get rid of things on both the reactant and the product side, so that's why a lot of times we put it above the arrow for a balanced chemical reaction. Now, this term called molecularity, Shakashiri does a really good job of going more in detail on this, so that's one of the lessons that you're going to do in their book. But this simply refers to the number of species that must collide, because remember, when you really think about chemistry, it's kind of like puzzle pieces. Atoms and molecules have to fit together in the correct fashion in order for a reaction to take place. A unimolecular mechanism will involve a step involving one species, bimolecular, step involving two, termolecular, refers to three. Okay, so a step involving three species. And again, I think they do a better job in Shakashiri. Now, an elementary step, let's get rid of that stuff, is a reaction whose rate law can be written just from knowing the molecularity. So remember, our rate law is going to be what order it is, and an elementary step kind of defines the whole system just from knowing the molecularity. So if you look on table 12.7, I'm not totally sure of the page number, but it kind of summarizes elementary step, molecularity. It's uni, so it's going to be first order. This one is bi, it's going to be second order. Now you've got more than one reactant, so here you have an A and a B. If they're both first order, it's still bimolecular, so here's your rate law. You've got another example of ter with two reactants, and then an example of termolecular with three reactants. So just different versions, at least the prefixes match up to the numbers here, so that helps make things, I think, a little bit easier to understand. Now, for a mechanism, a series of elementary steps that add up to give the overall balanced reaction. So the mechanism I kind of think of as all of the available, or all of the required steps that have to take place without canceling everything out. And it must agree with the experimentally determined rate law. So remember, we still have to determine rate laws experimentally, typically using the law, or the example method of initial rates, where you divide them and you use the log rules to get that exponent. So for rate determining step, it's one step in the reaction that is much slower than the rest, which makes sense by definition. If it's much slower, it's going to determine how fast everything else can take place. And so typically, it can be assumed to be the entire rate law because that's going to, remember, all the rate law does is tell us how fast things go. Now, if we assume the rate determining step is the second step in that original reaction that we had, then the rate would be equal to, lowercase k nitrogen trioxide and carbon monoxide. Since that's not the correct rate law, it has to be the first step. Okay, and when I say correct rate law, the rate law has to include something that is a reactant. All right, so for this one, it doesn't necessarily, remember, the rate determining step is just what influences the speed of the entire rate law. So the thing that can be confusing about rate laws is that you look at this and you go, okay, there's no carbon, there's no other reactant, and that's okay because it has to at least match a possibility. Okay, it has to at least match a possibility, and that's why, like I said, I think Schock does a little bit better job of explaining this. Most of the time, if this shows up, it's in a multiple choice question trying to predict what could be a potential rate law or a potential mechanism for things. Okay, and that's it. So I hope that helps, and we'll finish up with kinetics in the next